Okay folks, we're going to continue with chapter 19. We're still looking at right angled triangles, but this time we're going to think about the angles themselves. So I'll start off by saying this is very definitely a calculator topic. Make sure that you've got your calculator handy, and I want you to have a quick look and find three buttons. That is the one that says sin, cos and tan. That's where they are on the Casio. Those stand for sine, cosine and tangent, but I'm just going to call them sin, cos and tan. We need to do a little bit of a check that your calculator is set up correctly, because there are a couple of different settings these can be on in A level. So to make sure, I want you to type in sin 30 and see what you get. If you do it right, you should get a half or 0.5. If you stick in tan 45, you should get 1. If you don't get that, then you need to follow these instructions. Press shift, press setup, so that's these two buttons here. And then you need to select option 3, which will say deg. What that does is it changes your calculator to be working out angles in degrees, as opposed to some other weird exotic ways angles can be done in A level. The last button that I want to point out, although we're not using this week, but it's useful to make sure you know about it, is sin minus 1. If you look above your sin button, you should see a little sin minus 1. So that means if you press shift and then you press sin, you'll get sin minus 1 shows up. If you type in a half into there, we should get 30 coming out. And likewise, if you do tan minus 1, again press shift and then press tan, and then put 1 in there, you should get 45 coming out. Make sure you know how to do this, because otherwise nothing else is going to work. The second bit of preamble that we need to do is labeling sides of a right angled triangle. Now we've already talked about one of these, which is the hypotenuse. A hypotenuse is opposite the right angle. It's also the longest side. And I think that's something that you should be able to identify by now. Last time we just called the other two sides just sides because it didn't really matter. But here it does. We've got two types of them. We've got the opposite and the adjacent. And let's just go through those definitions quickly. The opposite is opposite the angle theta. So that means if we've got one angle labeled here, then the opposite is on the other side of the triangle for it. Where meanwhile, the adjacent is between the right angle and that theta. So our adjacent is over here. It's next to. So the word opposite obviously means opposite, the word adjacent means next to. It's all to do with this extra angle that we're adding in. So let's go through these three. Hypotenuse is always the easiest to do, so let's label that first. Hypotenuse, opposite the right angle, opposite the right angle, and opposite the right angle. And then let's think about opposites. So we want something that's opposite to the three labeled angles. They're called 75, 25, 40 this time. So our opposite will be over here. Our opposite would be over here. And our opposite would be over here. So that obviously leaves one side left to do, which is between the two angles. That's our adjacent. Notice I'm just writing in the letters of them rather than the whole word, because, well, there is not enough time on the earth to write that much stuff. So yeah, O, A, and H. Make sure you can label those sides correctly. So let's actually do some trig. So we're actually going to introduce three formulas today, and we're going to talk about a way of knowing which one to use in which situation. But for the first three slides, we're just going to look at each of those individually, so you don't have to make that decision. So we're going to use this formula to work out these missing sides that are labeled with X. And we're introducing a formula triangle, which works exactly the same as distance, speed, time, or density, mass, volume. You cover up the thing that you're trying to find, and that tells you what to do. So if I wanted to find sine theta, that tells me to do opposite divided by hypotenuse. If I wanted to find the hypotenuse covered up, that tells me to do opposite divided by sine theta. And if I wanted to find the opposite, it tells me to do sine theta times hypotenuse. Now, if we're doing this, your first step should always be to label the sides, and I'm going to add a little bit on, label the sides with letters and numbers on them. Okay, so there's going to be two sides that we label, and there's going to be one side that we don't. After that, all we need to do is to apply the formula. So let's look through these questions. Our first one, the two sides we're going to label are these two because they have letters and numbers on them. We are not going to label this side here. So x, that's our hypotenuse because it is opposite the right angle. 8, that's our opposite because it's opposite the 40 degrees. So we've got opposite is 8, we've got hypotenuse is x. We want to find x. So that tells us to do, if we cover that up on the triangle, opposite divided by sine theta. So what we can do is we can substitute in the things that we know. So x equals, opposite is 8, and sine 40. And that'll give us that side is 12.4 centimeters. Now, you know that's right because the hypotenuse should be the longest side. If you ended up with something that was smaller than 8, you know you've made a mistake. I'd like you to pause the video at this stage, have a go at trying to find the other 3, and then come back in 3, 2, 1. Okay, so let's go through. I'm going to label my sides. Hypotenuse is obviously the longest side. This is the opposite. It's opposite the 60. And I'm trying to find the opposite this time, which tells me I need to do sine theta times the hypotenuse. So I'll do that. I'll do sine 60, and make sure you close the brackets on that, times 50. Now if you type that into a Casio, it will actually tell you something like 25 root 3, but I would prefer this as a decimal, so we want to change that to 43.3. What about the second question, or the third question? Hypotenuse is 75, opposite is x, so we're trying to find the opposite this time. It means we need to do sine theta times hypotenuse again. It means we need to do sine of 55 times by 75. Again, make sure you close those brackets, and that should give you 61.4 centimeters. Notice in both those last two, we've ended up with a side that's smaller than the hypotenuse. That generally means we've done it right. Last one, hypotenuse is x, opposite is 20, and we're trying to find our hypotenuse this time, so we want to do O divided by sine theta. So we're going to do x is 20 over sine 59, which gives you 23.3 centimeters, longer than the 20, so we think we've done it right. Okay, that's the general idea. Now all the next two slides is nothing new. We're going to introduce two more equations which work in exactly the same sort of way, and all it means is you've got to label your sides a little bit differently. Let's do the first one together, and then I'd like you to have a go at the next three yourself. So let's see, first one we got x, that's our adjacent this time because it's next to the 70 degrees, it's between the 70 and the right angle. And our hypotenuse is 6, and indeed if we went round all the other triangles we could come up with a similar thing. We've got hypotenuse and adjacents on all of these. We want to find the adjacent on our first one, and according to our triangle that means we need to do cos theta times the hypotenuse. So we're going to do cos of 70 times 6, and we should get out of that 2.05 centimeters, smaller than 6, so we know we've done it right. Have a go at the next three, and I'll unpause in 3, 2, 1. Okay, for the next one we're finding a hypotenuse. That means we have to do adjacent divided by cos theta. So that is, let's see, we're doing x equals 15 over cos 75. That gives us a pretty horrible looking surd, but let's round it. It's 57.96 centimeters, or you could just have 58.0 if we're going to stick to one decimal place. The next one, again we're finding the hypotenuse, so we're going to do a over cos theta. That tells us that x is 28 over cos 48, which gives us 41.8 centimeters. And then for our last one, we're finding the adjacent this time, so we want to do cos theta times the hypotenuse, So that's cos 45 times 1.3, which is going to give us 0.92 meters this time for once, not centimeters. And then here's the third of our equations, which is to do with tan. Exactly the same thing, except this time we're looking at opposite and adjacent, no hypotenuse involved. Again, I'll do the first one, and I'd like you to try the next three. Let's think about labeling our sides here. Remember, the adjacent is always the one in between the right angle and the labeled angle. So here's our adjacent, and this is our opposite because it's opposite the angle, the labeled angle of 35. Let's do the same for the other triangles. So our opposite and adjacent, opposite and adjacent, opposite and adjacent. Make sure you understand why we're labeling one in each of those. If not, go back to the first slide. And then let's apply our formula. So we want to find the adjacent here. If we cover that up on our triangle, that tells us that we need to do opposite divided by tan theta. So that's going to be 10 over tan 35, which is going to give us 14.3 centimeters. In this case, we can't use the hypotenuse trick of we know it's got to be longer or we know it's got to be shorter. You have to kind of use your judgment about what the triangle would look like. This is right, but we have less hints with tan that we've gone wrong. For the second one, pause at this point, have a go at those three. 2, 1. Okay, for the second one, we want to find an opposite, and the opposite is tan theta times the adjacent. It's going to be tan of 22 times 18, which should give us 7.3 centimeters. For the third one, we want to find the adjacent, so again, we're going to do opposite over tan theta. We're going to do 2.8 over tan 31. It's going to give us 4.66, so I guess that would round up to 4.7 centimeters. And for the very last one, we want to find the opposite, so we're going to go again tan theta times adjacent. That means that we're going to do tan of 28 times 17. That gives us just 9.03, so 9.0 to one decimal place centimeters. Okay, hopefully that's getting a bit samey now because it is always that same method. Okay, so where does this word Sohcahtoa come into it? Well, Sohcahtoa is a way of identifying which is the correct triangle to use on a given question, because you're not just going to be given a sheet of sine questions, cos questions, tan questions. You're going to be given a right angled triangle and asked to figure out a side. Obviously the connection there is that if we have our Sohcahtoa, that's exactly what these letters spell out if we read them sort of in this rainbow fashion. We've got SOH for sine opposite hypotenuse, cos AH, so that's the Ka, and TOA for tan opposite adjacent. That's our Sohcahtoa. Now, let's actually go through the process of doing this on 3 different triangles. There are 2 steps essentially that we have to add to what we did on the previous slides. The first one is we need to label our 2 sides of interest. Now, when I say a side of interest, I mean that it has a letter on it, or it has a number on it, or possibly it's mentioned by the question. If it doesn't have any of that, we don't care about it. Sohcahtoa relies on 2 sides and an angle. So let's look here. We've got X, that's a side of interest because it's got a letter on it. It's clearly the hypotenuse because it's opposite the right angle, so we'll call it hypotenuse. And 3 is in between our labeled angle and our right angle, so it's our adjacent. If we do the same with the other triangles, 9.3 here, that is opposite the labeled angle, so that's opposite, whereas X is between the labeled angle and the right angle, that's our A. For the last triangle, 4, that's the hypotenuse, it's opposite the right angle, and X is opposite the labeled angle, so it's O. So what we do is we look at, say, our first question here, which has H and A in it, and then we look for the triangle that uses H and A. And there's only one triangle that does, which is the cos triangle. So we'll write that down. This is our second step now. That's our K of the Sohcahtoa, and that's the one we're going to use. Now we're trying to find the hypotenuse, so we cover that up, and that tells us that if we want to find the hypotenuse, we do adjacent divided by cos theta, and then we can stick in the things that we know. We know this is 3 divided by cos 25. If we type that in, we'll get that x is 3.3 centimeters. So yeah, you need to label two sides, pick the right triangle, and then just do the calculation same as we did on the previous pages. What about this second one? The second one uses O and A. Which triangle uses O and A? It's the tan one. So tan theta, opposite, adjacent. We're trying to find an adjacent, so that would be opposite over tan theta. So x is equal to 9.3 over tan 30, which is 16.1 millimeters this time. For our last one, O and H, that's the sine triangle, because that's the only one that has O and H in it. So I'll write it down. We'll say we're finding the opposite, so we need to multiply the other two things together. So O is equal to sine theta times H. So x is equal to sine of 60 times 4. So that's going to give us 3.5 kilometers this time. So yeah, label your two sides, pick your triangle, and then it's exactly the same as the previous couple of pages. Nice one. Now at this step, I'd probably say stop, have a look at the Hegarties, and then come back to this because we're going to look at some more advanced applications. We're going to start with some multi-step problems. These are similar to the Pythagoras multi-steps in terms of you do one triangle and use it to work out the other. Here we want to work out x, and the problem with this triangle is we don't know any of the sides. We need to know two sides for Sohcahtoa to work. So what we're going to do is we're going to look at this triangle up here first. So we're going to break this down. So we've got 50 and we've got 5, and we're going to work out this side here because then we've got a side on the other triangle. So we've drawn it. Let's label up our diagram. So we've labeled the adjacent is 5 and the opposite is H. Now that's O and A, so that means that we need to use the TOA triangle. That's tan theta, opposite and adjacent. The opposite is what we're trying to find, so according to that we need to multiply tan theta by the adjacent. So y is going to be equal to tan 50 times 5. It's going to give us, let's go to slightly more decimal places this time because we are going to use this answer again. Let's go to 5.96. And then we can consider the bottom right angle triangle. We've got an angle of 38. We've got this x that we're trying to find, and we've got this 5.96 that we have worked out. So labeling our sides, that would give us opposite and adjacent. So what could we do here? We want to find the opposite. So actually again, we're going to do tan theta times adjacent. This is another TOA triangle. So x is equal to tan 38 times 5.96, which is going to give us, let's stick to two decimal places, 4.66 as our final answer, centimeters. Now a more advanced application we can do here is we can use it to find the area of a parallelogram. Now a parallelogram area is base times height. I'm sure we've mentioned that before. And there doesn't seem to be a right angle triangle here, but we can make one. We can draw in a relatively straight line here. We can stick in a right angle on the corner, and we can just consider this because that is our height. So let's draw that part enlarged. We've got a height here, we've got 7 here, we've got 50 here, and we need to go through the same process as always. Label our sides. There's our hypotenuse. This one's our opposite this time. So we're going to be using SO, so sin theta opposite hypotenuse. And we need to find the opposite, so we're going to be doing sin theta times the hypotenuse. So that's going to be that our height is sin 50 times 7. That means the height of our parallelogram is 5.36 centimeters. We still need to find the area, so we'll then do base times height. We'll go 10 times 5.36, and we'll get that it's 53.6 centimeters squared. Another application we can do here is we can find the perimeter of a right angled triangle. Let's label up our sides. We've got the opposite, and we've got, we don't know which side we want to do. Let's work out this one here first. Let's call that the adjacent. Then we can use the Toa triangle. So if we want to find the adjacent, that's going to be equal to the opposite divided by tan theta. That's going to be x is 12 over tan 70, which would give us 4.37 centimeters. And then to find the other side, I can call this y. We've got a couple of options. We could actually do Pythagoras here. We've got a side and a side. We could go 12 squared and 4.37 squared and get the hypotenuse squared. But as this is the trig one, I'm going to stick with the trig. I'm going to delabel the x, and I'm going to say that, well, these are the two sides I'm interested in now, and that's the opposite and the hypotenuse. So that means if I want to work out y, I'm going to have to use SO, sine theta, opposite, hypotenuse, trying to work out the hypotenuse. So that's going to be the opposite divided by sine theta. So y is equal to 12 over sine 70, which is 12.77. Now go back to the question. We want to find the perimeter of our triangle, so we need to add those three sides together. So 12 plus 4.37 plus 12.77 is going to give us 29.14 centimeters. Cool. And then the very last one, I've taken this from a GCSE paper. I'm going to find the area of this equilateral triangle. Now this looks even more obtuse than the parallelogram one in that there's only one side labelled and there's no actual angles. You could do this with Pythagoras. In fact, I think we've done this with Pythagoras last week, but I'm going to do this with a trig way. And I'm going to use the fact that I know angles in a triangle add up to 180. I know equilateral angles are all the same. So I know that this angle here is 60. Now if I want to find the area of a triangle, I need to do half times base times height. So I definitely need to find this height here. And here's my right angle. So there's the triangle that we're going to be considering. We've got a right angle there. We've got 60 here. And we've got, well, we could do a couple of different lengths here. Let's use the hypotenuse ones. Let's say this side is 10. We know this is equilateral, so we know that's 10. If I want to find the height, let's label up our sides. We've got opposite and hypotenuse this time. So that means we're going to use SO. We're going to use sin theta opposite hypotenuse. If we want to find the hypotenuse, find the opposite rather, we're going to multiply those two things together. So that means we're going to do sin 60 times the hypotenuse times 10 to get our height. And that's going to be 8.66 centimeters. And then we can go for the area. We can go a half times the base. Now remember, the base of the whole triangle is 10 times the height, which we worked out. And that should give us a final answer of 43.3 centimeters squared. So yeah, application.